Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, good afternoon, everyone. My name is Rustin Leno, and it's my great pleasure to introduce our speaker this afternoon, Jean-Ramon Abrial. Abrial has defined a number of formalisms that we're used to, the Z notation, the B method, and what he's going to talk about today, the Event-B. Each one of these, or the B and Event-B, give you ways to develop programs starting from specifications and models and going downwards, stepwise refining your programs. And as are described in his new book here too, which I'll make sure to flash. And these techniques have been used by Jean-Ramon and others, for example, in the Paris metro system to prove some safety critical properties and other systems. So he's going to teach us more about how to use the method.
Good afternoon. Rustin, thank you very much for your introduction. So I have the pleasure to start this Event-B course with a short introduction, only 2 or 3 slides, and then we go on to our first example. So let me just set up the scene. The purpose of the course is to show that software and system can be correlated by construction. So this is a very, very important thing, and give some insight on modeling and formal reasoning using this formalism called Event-B. And to show also that this can be made practical with the Rodin platform. I'm not sure we will have time to have practical session with the Rodin platform, but it is a free software, so you can also download it and use it. And essentially what I will do is to cover some examples. So I've put a few of them. Probably have not enough time to treat all of them. Controlling cars on a bridge. I think this will be today and probably part of next time. A mechanical press controller. A mechanical press is a very basic machine, but you'll find out that it is not so simple and pedestrian as you can imagine. And then a file transfer protocol, a routing algorithm, and the development of classical sequential program, ... But I'm pretty sure that I will not reach the ... part. Okay? What you will learn is by the end of the course, I have the pretension to say that we'll be more comfortable with modeling versus programming, makes the clear distinction between the two, and the very important notion of abstraction and going the other way around, refinement. I've put within brackets these things because I will not cover this because I will not have enough time. By the way, these slides will be made available to you, and also the Chapter 1, which is the introductory chapter of the book, and Chapter 2, which covers this example. So the text will be a little more elaborate than what I will say in the slides. So there is no problem. You can have access to this. Please do not distribute too much these things, because otherwise I might have some problem with Cambridge University Press. So this is the introduction is finished, and now we go to number 2. Number 2 is this problem of controlling cars on a bridge. So I will describe this system. So the idea is to present a complete development of a little system, and the approach will be to have a series of model more and more refined until we get something that could be translated into code. And this approach is called refinement. And the idea of the model is to formalize what an external observer could see of the system. So it's completely different from programming. In programming, we just instruct a computer to do something. Here, we are going to, as engineers, we are going to suppose that we see the system, this controlling card. We see this system, and we observe it. And we observe it more and more and more and more carefully. So that, the result of this observation precisely is to build some models. Okay. And at the end of it, we just jump into programming, saying, but the model now is so concrete that it can be transformed to a program. So you see this idea of being correct by construction. What we define, what we build are models, not program. Model which will be larger than the strictly speaking piece of software. This will be a model of the entire system. And so with each refinement, the observer zooms on some more details. So the purpose of this lecture, number 2, prove that each model can be analyzed and proved to be correct with proof. And as I've said to some of you last time, the mechanics of proving will be exactly the same thing as the mechanics of debugging by testing. So we have the model, we do not execute the model, but we prove the model. And again, the aim is to obtain something that is correct by construction. And the correctness criteria will be formulated as proof obligation. And I will describe more carefully what exactly are these proof obligations. So I will not cover these two, again, for the same reason I have said before. What you will learn, the concept of state and events. We are not programming, so there is no loop, there is no ifs and else. There is just assignment and bare guarded commands. And so these are the events and the state on which we are working. And we will learn some principle of system development, essentially the notion again of invariant and refinement. So I think there is no need here to have a refresher on classical logic and no need to have a refresher on formal proofs. So the outline, this is systematically followed when doing some development. First of all, writing down a requirement document so that when we start the development, we know exactly what are the requirements. And I insist, last time also I insisted on this. This is very, very important, and especially in industry, these things are not very good. So it's very important to write down very, very carefully this requirement document. Then we define a refinement strategy. We are going to see how we are going to use the requirement little by little in order to eventually get a more and more concrete model. And then number 3 is the development of the initial model and then the refinement. So this is the outline. So the requirement document. So let me describe this system in a very general way. So this requirement document will be made of 2 texts embedded in each other, some general explanation, plus some well-defined boxed requirements. So we are going to, and this requirement will be labeled, so they will be concerned either with the equipment of the system or the function of the system. So the system we are going to build is a piece of software connected to some equipment. This is very, very classical. And the function of this system is to control car on a narrow bridge. But I will explain what I mean by controlled cars. And the bridge is supposed to link the mainland to a small island. So. So we have our first very general function. The system is controlling car on a bridge between the mainland and the island. So you see here, I repeat in some of the requirement, I repeat what I've said, but at the end of the definition of the requirement document, we'll have a list of very well-defined requirements, and we could forget about this. So this can be illustrated that way. We have the mainland, the bridge, and the island. the controller is equipped with 2 traffic lights with 2 colors, red and green. So this will be described here. We have a traffic light here and a traffic light here, and they are both situated at both ends of the bridge, and this is illustrated as follows. So what I do again here also is to introduce things little by little. So we have the mainland, the island, the bridge, and now the two traffic lights. Again, we go a little more formal here. The traffic light controls the entrance to the bridge at the both end of it. So it's equipment number 2. And equipment number 3 is absolutely fundamental. This is an assumption about the equipment corresponding to people. In fact, with a car, driver is supposed to obey the traffic light by not passing when the traffic light is red. Okay, so we have this, and it is very important because it means that if this is not true at some point, then the system could crash or have a problem or difficulty. So this is an assumption which makes very, very clear under which case we consider that the system will be correct. Okay, so cars are not supposed to pass on red traffic light, only on green one. So this is an assumption. We have also some car sensors, and they are supposed to detect the presence of car intending to enter or leave the bridge. And there are 4 such sensors, 2 of them situated in the bridge and 2 others situated on the mainland and the island. So this is equipment number 4, and you can see the drawing. Yeah, you can see the drawing here. So now we have the sensors here. So car, we are supposed to drive on the right hand. When I present this in Britain, so there is a problem. People are confused. Okay, so we have sensors here. We have a traffic light. So a car is going here, and again the sensors can enter, and the same for going out. And now we add the 2 main functions of the system, which are the following: the number of cars into the bridge and the island is limited for some reasons. And the bridge is so narrow that the bridge is one way or the other, not both at the same time. So cars cannot cross each other on the bridge. Okay? So that's it. We have 3 functions. The first one was very general. We have lots of equipment. We have 6 equipment. And we have these 2 functions. And that's it. And now we can remove all this text here, put all these things together, and this is the law. This is the law. And we, at the end of our development, we are going to check that we have indeed taken into account all these assumptions for equipment and all these functional requirements for the system itself. Now, the next step, yeah.
It doesn't say anything in there about progress. So couldn't progress. So you could imagine a system that just didn't let any cars pass across the bridge ever.
Yeah.
Right? And that would be correct by this construction according to these functional requirements?
Yes, you're right. So we have to say something else. I agree with this, that it is indeed possible for cars to go in. Okay, and you will see how we'll solve this problem. Okay. But thank you. That's a good point. The refinement strategy. The role of the refinement strategy is to define a priori, without starting, the various steps, and linking each step with the requirements. So we say in first step we take this one, second step this one, and also the goal of the refinement strategy is to start the traceability of the requirements. So we can say at this point we have taken into account this requirement, we can tick it, and at the end we have to be sure that we have ticked all of them. And of course we feel possible. It would be possible to modify some of the requirement during the formal development, because we might figure out that. Because they are not formal, we can figure out that some of them are impossible or bad, or that we could possibly change them. So here is the refinement strategy. There might be some others, but this is the one I have chosen. I've chosen to be interested in limiting number of cars, fun2, okay, in the initial model, and the first refinement introducing the one-way bridge. So the fact that the bridge is one way. And as you see here, I have not introduced the traffic light and the sensor before the second and third refinement. So in fact here, what we do something abstract, and we suppose that there are some guru or intelligent mechanism that can make the thing working correctly. And here we say, but this is not the case, so we have to add some equipment, the traffic light, and then the sensors. Okay? So let me now enter the formal development, our initial strategy. So limiting the number of cars, fun2. So this model is, as usual in abstraction, is extremely simple, extremely abstract. We completely ignore the equipment. We do not even consider the bridge, so there is no bridge. We are just interested in the pair island bridge. And we are focusing on fun2, limiting the number of cars on island bridge. So the sort of paradigm is we are very high in the sky, and we do not see the bridge. We just see the mainland and the island, and we want to just define something that will take into account this fun2, that there is a limited number of cars on the island bridge. So that's the idea of the initial model. So this is the drawing, no bridge between the two. And we have this compound here called island bridge. Okay? So we have now to define the dynamics. We have essentially two events, two transitions. You remember, we are considering only transitions. And we have two transitions, ML out, mainland out. So a car is going out from the mainland, and ML in, coming back to the mainland. So we have two events. So we are going to define these two events. First of all, define the static part. We have a constant D, which is a natural number, and D is the maximum number of cars allowed in the island bridge. So in defining a model with Event-B, you have the static part, which is called context in Event-B, where you define all the constants. And here we have a single constant and with a single axioms. And then we'll define the dynamics now. Essentially, the state, which is dynamically changed, and the various events. So we have a single variable n. N is the number of cars in the island bridge. And then we have this, it's a natural number. And we have the basic invariant here that n is smaller than or equal to d. And this takes account of fun2. The number of cars is limited. N is the effective number of cars in the island bridge. I'm sorry, it's so simple. It's so trivial at this level. But you will see, it will become a little more complicated later, and we'll find some problem. So now we have the story about ML out, mainland out. So we look at before and after, like in a whole logic, so to speak. Before we have a car here in the mainland and the ML out, and then this car is now inside the island bridge. And so the number of cars in the island bridge is just incremented. And ML in, back to the mainland, it's exactly the opposite. The number of cars in the island bridge is decremented. So it's totally trivial. We can define very simply our two events, just an incrementing and decrementing. So ML out is just defined this way and this way. Oh, be careful, these are not programs, these are models. Okay, this is the way this transition works. N becomes n plus 1, n becomes n minus 1. And an event is denoted by its name here and its action on the state, which is either in this case incrementing or decrementing. Okay? Oh, this is I said here, this is an approximation Why is it an approximation? This might be refined later, so be richer. And it could be wrong also. That might be insufficient at this stage because not consistent with the invariant. Because we have defined the invariant, okay, n smaller than or equal to d. And then we change our hat and we define the dynamic, nn plus 1, nn minus 1. And now we have to reconcile the two to see whether the transition is consistent with the invariant. And so we might have, we have to do a proof here, very simple proof, and we might discover that we have some problem. So let's continue. So the invariant, the definition of an invariant, it's a constraint on the allowed value of the variable, here n smaller than or equal to d. It must hold in all reachable states of the model. So to verify that this holds, we have to prove that it holds in the initial state. I have to define the initial state. And the invariant is preserved by all events. So we have to prove that this is preserved by all events. And so we will formalize these things by proof obligation, POs. So these proof obligations are completely systematic. And we need a rigorous proof showing that each proof obligation indeed holds. So towards the proof, we define, together with the action of each event, before-after predicate. It describes the relation between the value of the variables just before and just after the event occurrence. The before value is denoted by the variable name, and the after value is denoted by priming the variable name, n prime in our case. So it's completely trivial here. Nn plus 1 gives a before-after predicate n prime equals n plus 1, and nn minus 1 gives n prime equal n minus 1. So by doing this little jump here from colon equal to equal by introducing the prime here, we can enter into mathematics. We have no more something becomes equal, which looks like programming, and now we can define clearly the proof obligation. So let me do this. So here are the before-after predicate. The after value is defined as, in this case, just a warning, that in this case, n prime is defined as a function of the before value. This is because the two assignments, nn plus 1 and nn minus 1, are deterministic, but it could be also possible to have non-deterministic events, and we will not have this into this example, but in further example, we might have this. So this is not necessarily the case that we are always deterministic. And now our intuition about the proof obligation. For example, this invariant, n is a natural number. We consider ML out. This is a before-after predicate. And we have to prove that the invariant here is kept. Therefore, we have to prove n prime belongs to the natural number. And n prime is just n plus 1. This is an assumption. And therefore, we have to prove this. We have to prove that under this hypothesis, we can have this. Not very difficult. Piano axiom. So this is what we have to prove. And this is put under the form of a sequence. You see the turnstile here, all the hypotheses. We have only one here. And here the goal or the conclusion that we have to do. Okay, so here at that point, when I'm doing the course, in a more general way, I introduce the Peano axioms and various axioms in order to do this proof. Okay, so the general form for this invariant preservation proof obligation is the following, in a vertical way. Under the axioms and the invariants as assumptions, I have to prove for each invariant that the modified invariant, modified by the before-after predicate, is still true. Okay, so this is so now this proof obligation will be part of a tool of a plugin into the Rodin platform, which will precisely be the proof obligation generator. So what the proof obligation generators, it analyzes the events. it transforms the colon equal into the before-after predicate and generates, according to this, generates all the proof obligation of all the things that are to be proved and pass all this to the prover that is supposed to do this proof. So it's completely systematic. The tool is defined under Eclipse, and Eclipse is quite nice because there are lots of possibility to do things automatically with Eclipse. Okay, so here are the four proofs. We have 2 events and we have 2 invariant. Therefore, we have 4 proof obligation. Do you have an idea about this proof obligation?
2 will work, 2 won't.
Yeah, these 2 are, we have a problem. This one, no problem. This one, no problem. But here we have a problem because when n is equal to d, n plus 1 is not smaller than or equal to d. And here when n is 0 and minus 1 is not a natural number. So we have a problem here. We discover that our events are no good because of this. Okay, so we have to solve this difficulty. Here, in fact, we would like to have that n is smaller, strictly smaller than d. And here we would like to have that n is positive. Okay, and then n minus 1 is still a natural number. So there are clearly 2 assumptions that are missing. 2 assumptions that are missing. Let's add them precisely. These are the 2 assumptions. Let's add them to the events. And so now we transform the events by adding to them guards. And so these guards are here for this one and here for this one. And these guards, if you think in terms of an execution, these are the necessary conditions for the event to occur. And of course, in the proof obligation, now because necessary condition for the event to occur, therefore, in the proof obligation, we are going to add, for each event, we are going to add its guards. So we modify our proof obligation into this one, axiom invariant, guards of the events, and modified invariant. Okay, so the idea here was to introduce in a gentle way the notion of guard. So be very careful. A guard is not a precondition. Okay, a guard is not a precondition. A guard, and you will see that they work in a completely different way as far as refinement is concerned. When you have pre-post condition, when you refine, you can weaken the precondition because you can buy something that is more expensive. Okay. Whereas for a guard, when we refine, we strengthen the guard. We make the guard more precise. Why is that? That's very obvious, because we introduce more things. Therefore, our abstract events now have to be made narrow because we add new features or new functionalities in our system. So keep this in mind. A guard and a precondition are some sort of dual concept. Again, by refinement, you weaken a precondition. By refinement, you strengthen the guard. Okay? And here, we are not so much interested in precondition because, again, we are not programming. When you program, you need to have precondition protecting a piece of code, because the caller, the people who call this thing, they want us to prove and be sure that the people who call these things are within the precondition. Okay. Whereas for a guard, if the guard is false, if the precondition is false, crash. The system cannot continue. Whereas when a guard is false, wait. Okay, wait. The thing is not cannot occur. Just the thing cannot occur. And why we have that? Because again, we observe a system that is existing in our head. Of course, we observe the system, and little by little, we are going to make more and more precision in this observation. So we are not interested in this approach. We are not interested. We will be eventually, of course, but we are not interested primarily in the notion of precondition, but far more in the notion of guard, because again, we are going to refine by making more and more features into our system. Yeah?
These events are executed atomically, right?
Yeah.
And so the only specification that we have right now about the consistency of the events is the invariant.
Yeah.
Do you also have some notion of local invariants? Or this invariant is completely global, right?
Yeah, they are completely global. Yeah. No, there is no notion
No
of...
notion of a local invariant.
No. The sort of local thing is the guard. Okay.
Yeah.
So you see, it's written here, when you prove something, you have all the invariant, the global golden rule, plus the special thing concerning the event, okay, as an assumption, and then under this you prove the modified invariant. Okay?
Right.
Okay?
Yes.
So let me proceed. So here is the new proof obligation, and now I've added the guard according to my proof obligation, and now of course the proof are that easy.
Maybe I'm jumping ahead of the game, but at some point we have to jump to programming, right?
Yes.
Then we have to implement the guard somehow.
By precondition.
I see. At that point, we'll introduce the precondition.
Yes.
I see.
Yes. We jump.
Okay.
A missing requirement. It is possible for the system to be blocked if all these guards are false. So that means deadlock. Okay. And we have to prove that in our case that this is not the case. Because we want that to be, we do not want that to happen, and we have, by the way, we have forgotten something. Once started, the system should work forever. Okay, there is no reason for the system to halt. So you see also here, the main thing we want to do is not just defining a program that does something and give a result. It's a program that controls a situation. Okay, and we do not want that program to stop. So we add fun 4 here. Once started, system should work forever. And so we have to prove that indeed our system is deadlock free. If we had no guard, there is no problem. But now we have guards. So it might be the case that in some situation these guards are too strong, and the system becomes deadlocked. So we have to prove the deadlock freeness. And under the axiom and the invariant, the disjunction of the guard is true. Okay? And therefore, if it's always true, therefore the system is deadlock free. And it's very easy to do this. We have this. We have this invariant. So n smaller than or equal to d can be replaced by this. So we have a proof by case. This case is easy because we have this here. But when n is equal to d, we cannot prove it. Okay, what happened?
We need to say have a lower bound on
On d. Because we have said just that d is a natural number. If d is 0, the system doesn't work. There is nothing happening. Okay, so it's amazing how when doing this you discover little thing where you've made mistakes. Okay, we have made this mistakes of defining the axiom for the limit, the upper limit of the number of cars in the island and bridge, and so we have to correct this, and so we have to introduce another axiom which is for d, which is d is positive. Conclusion: thanks to the proofs, we discovered 3 errors. We were correct them by adding some guards, adding an axioms, and here we see just right in this little example the interaction between modeling and proving. You see, we go from one to the other. We found out the problem. We go back to the model. We add the guard. We go back to the proof. We let log free. We find a problem, so we add an axiom. So this back and forth is extremely important, and the prover must be a tool which helps us doing this back and forth. Okay, this is not a tool that proves a beautiful theorem. This is usually very simple and very pedestrian theorems. but they help us doing this debugging our construction of the model. So we define proof obligation. I've not defined this one, but it's very trivial. You can see it in the text, the invariant preservation and the deadlock freeness. And this is the form of the proof obligation, which are, again, the basic ingredient, the basic elements of the proof obligation generator. I recall you, as I've said already, the system, the platform ingests the definition of the model. If it's correct syntactically, pass it to the proof obligation generator. The proof obligation generator generates all the proof obligation and pass the proof obligation to the prover. Okay. And yourself, you are sitting, but it goes so fast for a system like this that either you get an error or the prover say, I can't prove, and then you have to scratch your head and say, yeah, there is an error somewhere, I have to modify it, go back to the model, and go back then to the proof. The summary of the initial system is just this, okay? And the two axioms, the two invariants, the two events, and the initialization. There is no cars anywhere. First refinement. So now we have solved the problem of limiting the number of cars, but this was on a very abstract situation where there was no bridge between the two. So now we are going to introduce a bridge, okay? And the fact that it is a one-way bridge. We refine completely, not the program, we refine the entire situation because the bridge is not part of the software. The bridge is part of the global situation. So we are not introducing the sensors or the traffic lights, but we are introducing now just the bridge. So the sort of paradigm is that we were very high in the sky, and now we go down with our parachute and we see more things. Our view of the system is more accurate. We see the bridge separating the mainland from the island. We refine the state and we refine the events. And we are going to add new events to the two we have, ML in and ML out. And I told you last time that refinement is not only adding things to the state, but also cutting the time grain at which we observe our system. Now we can observe our system more accurately, and therefore we will introduce new events which can modify things also. So this is the situation. We have ML out for cars going out from the island, from the mainland, but now they go onto the bridge, not directly onto the compound because we have separated the two. And then when the car arrives here, we have IL in coming into the island, IL out, and ML in. So in red, the emphasized ones are the new ones. So we are going to also discuss the status of these new events and also the status of the old event that we refine. Okay? So let's go. And now we are going to introduce a new state. So we are going to introduce three values, A, B, and C. A is the number of cars on the bridge going from the mainland to the island. B is the number of cars on the bridge, on the island, and C the number of cars on the bridge going from the island to the mainland. A, B, and C. And of course, we have to relate A, B, and C with N, the abstract thing we have before. So we have a so-called gluing invariant. We are going to glue the concrete state A, B, C with the abstract state N. And we have also to take account of the fact that the bridge is one way. So A, B, C are natural numbers.
I thought that the N was the number of cars on mainland.
So,
outside. Oh, it was outside mainland. Sorry.
N is yeah. So here is the connection. A plus B plus C is equal to N. And N is not a variable anymore of this refinement. It's a variable of the previous of the abstraction. But in the invariant, we have the right to mention this, and precisely this is the connection, and we used to call it the gluing invariant. We glue the concrete to the abstract. And here it's a one-way bridge, A is 0 or C is 0. Okay, they cannot be positive together. And that's it. That's it. So this is the new system. So here again, invariant. This invariant are the concrete invariant. Okay, and this invariant is again this is the gluing invariant between the abstract value n, abstract variable n, and the concrete variable a, b, and c. Okay. And now we have to propose some new things for the event that existed in the abstraction, ML out. And here we propose this: when C is 0, if C is not 0, we cannot go because of the one way of the bridge. And A plus B plus C is smaller than D. So then we can enter because we have not reached the maximum, and then A plus 1 we just add one car here. Yeah.
So why were we able to delete the previous updates to n and the previous guard on n?
I'm going to explain that. And we have the same thing for ML in. If C is positive, so there are some car here, then C becomes C minus 1. And of course, the question you ask, you could also ask it here. By the way, the before-after predicate, now we have several variables. So the before-after predicate, for example, for this is A prime is A plus 1, but we have to incorporate B prime is B and C prime is C. Okay, but this is done behind the curtain by the proof obligation generator that does this, and the same thing here, we do that. So this is convenient to have this writing here because it's not necessary to say when something is not mentioned, it's like in programming, it is not modified. Intuition about refinement. So we come slowly to your question. The concrete model behaves as specified by the abstract model. So the concrete model does not exhibit any new behavior. Okay? It's a correct simulation. And to show this, we have to prove that every concrete event is simulated by its abstract counterpart. I will define this. And we have also the same sort of thing for the initial statement, for the initial case. And we will make these two conditions more precise again, as proof obligation. So let me here show precisely next to each other the abstract event ML out and the concrete event ML out. So let's have a sort of an intuition. So here, when A plus B is smaller than D and C is 0, is it the case that we have n smaller than D? Yes, because A plus B plus C is equal to n. So A plus B plus 0 is smaller than D. So we are happy here because this guard implies this guard. So it means that when this is true, when this event can occur, this was also the case for the abstraction. And here, rather than having n plus 1 as in the abstraction, we have A plus 1. And B and C are kept 0. So therefore, because A plus B plus C is equal to n, clearly when we do this, that corresponds to this. Yes, question?
This invariant n is equal to A plus B plus C. You just assumed it. What's the justification for it?
The justification, let me go back here. Here. Okay. Before, in the abstraction, we had n, which was on the so-called compound island bridge. N was the number of cars in this, and now we cut n into pieces. Okay, the cars that are here going here, the cars that are here going here, and the cars that are here. So the justification is that we have a situation, we have a zoom, we have a situation which is more precise. We have A, B, and C, but it must correspond to the abstraction. So therefore, certainly A plus B plus C is equal to N. I'm not convincing you.
No, I think that there's a missing step. There must be a case where right after there must be a place where there exists a program that contains both N and A and B and C, and the events are updating all these variables, and then you must have to show that the invariant N is equal to A plus B plus C is maintained.
Yeah, you could have that, but this is precisely refinement. That it is not needed to have A, B, and C and N together. Okay, we have N in the abstraction and A, B, and C, and I will show you in a minute the diagram that explain what refinement does. Okay, so postpone a bit if you have any more problem. I will come on to this.
So just one more question.
Yeah.
That the enabling of the action is not changed by going to A plus B equals C, right? But before you said we are allowed to strengthen the guards.
Yes, yes.
So can I do both at the same time, or is it not? Is there some source of?
No. You can do I was not completely correct. You can strengthen the guard. The only thing that you have to prove is that the concrete guard implies the abstract one. Okay, so you have strengthened the guard. Okay, but we will see that might pose some problem. We will come back in a minute on those problems. But before I have to go here to his problem. So here this is the diagram. We have a concrete event. We have an abstract event. So this, in our case, the abstract event was working with N. And the concrete event is working with A, B, and C. And here we have the gluing invariant. So the intuition of the refinement is that it's exactly what you say. We suppose that together the abstract and the concrete event are working together, that the N and the A, B, C are on the same box. Yeah. Okay. And what we have to prove is that the gluing N equals A plus B plus C is maintained by these two people going together here. Yeah, okay, now you see? Yeah. Fine, thank you. I'm happy that you see. Okay, we will go back to the strengthening. So the proof obligation of guard strengthening is just this. The axioms, abstract invariant, concrete invariant. So we have the concrete and the abstract. The concrete guard, and then the goal is to prove the abstract guard. So the concrete guard are stronger than the abstract guard. Now, there is a big problem. They could be so strong that they could be false. Okay? And in this case, we have a deadlock in the concrete world. Okay? So we have to do something about that in a minute. So we can prove this. And then we can prove this. So we start to, of course, in the more detailed slides, this is proved, and in the text that you have the possibility to read, everything is proved. And we have the initialization, of course. They are all initialized to 0, and we have a concrete another. Proof obligation for initialization. I just go a little fast here. And now we're going to add new events. Okay. The new events is IL in and IL out. So we were dealing with ML in, ML out, the old events, and now we have these new events here. So what is the status of the new events? What do they represent? They represent the fact that we from the abstraction, we see more things. Therefore, there are more things that move. We have more transition now. So we have to be extremely careful about yeah?
Sorry, I think I missed something. So we said we have to prove that the guard is stronger than the abstract guard. But did we say anything about the invariant? Does the abstraction invariant still hold after the step in the concrete now? That is the n equals a plus b plus c.
That was the refinement check he was talking about.
Yeah, the concrete. So we do that too, right?
Yeah,
he didn't have a separate slide on it.
Yeah. So adding new events. So new events are transitions that have no abstract counterpart. They are kind of internal steps with respect to the abstract model. They exist in the reality, but they were not being able to be seen in the abstract one. And now the observer can see them by zooming. And we have a temporal refinement because now rather than having 2 transitions, we will have 4 transitions. So the system is a little more complicated. So we have to see what we are going to prove for the new event. So let me just show this event IL in. If A is positive, then A becomes A minus 1 and B plus 1. So the car moves from the bridge to the island. And similarly, this one is when B is positive and A is 0, so there is no car coming in from the mainland to the island, then BB minus 1 and CC plus 1. Okay? And yes, here we have several actions. So the before-after predicate is just all these 2. So the idea of refinement. So this new event, they refine something. What they refine is precisely some sort of implicit event that do nothing, because in the abstraction it didn't exist. So there was no change in the abstract variable by these events. And when we make the refinement, we enter into the concrete state. So these events, these new events, they should refine skip. Okay, they should refine something that did nothing in the abstraction. So this is, and the guard strengthening is very obvious because skip, which is here the before-after predicate, has no guard, so there is no problem, and we are just to prove the invariant. So the refinement, so the proof obligation for the new events. So guard strengthening is trivial. We need to prove invariant refinement. But the new event must not diverge. You see, when we introduce a new event, we might have funny pathology because these new events could take control forever, never allowing the old event, the poor one coming from the abstraction, to be filed. Okay, so we have to be sure that it is not possible for the new event to go forever. So we have to prove that they somehow, if we stop the possibility of the old event to be enabled, that the new event goes to deadlock. They cannot go forever. Okay, so for this we have to exhibit a variant, which is a natural number or anything more complex, well-founded thing, and that each new event decreases this variant. And the variant is the same for all the population of the new event, because if otherwise they could play ping pong. And we want to be sure that the entire population of new events, they decrease this variant, so that eventually the old events could be executed. Okay, and it's exactly what we need. The new events are some sort of extension that was not possible to see in the abstraction, and we accept that this exists in the concrete, but of course they have to be polite and they have to not to diverge. So this is the first pathology. The new events diverge, and we will see later on another pathology. So we have to prove more things. So we have to define a variant, and which is a natural number. And we have to prove that the variant is systematically decreased by some new events. So in that case, the variant is 2a plus b, and it is easy to prove that the variants are indeed natural number and they are decreased. And now we have to prove something important, which is notion of relative deadlock freeness. And that corresponds to the second pathology, which could happen. There is no new deadlock in the concrete model. That is, all deadlock of the concrete model are already present in the abstract model. Okay, which means that what we have introduced, because we have strengthened the guard precisely, we have not strengthened them so much that we block the system in the concrete, whereas it was not blocked in the abstract. Okay, we have to have the same behavior, global behavior of the system. So it's called relative deadlock freeness, because it might be possible, it's not the case here, but it might be possible that in some occasion the abstraction deadlocks finish. Maybe there are some infinite paths, but there are also some paths that finish. And what we have to prove is that the concrete does exactly the same thing. So it does not deadlock more than the abstract.
But
it's
you
called,
started out saying that the abstraction is deadlock free, right? We checked that.
We check that.
We know that there are no deadlocks there.
Yeah.
So then why, when we refine, we can just make sure that there are no deadlocks in the new system, right?
Absolutely.
So why do we need this relative deadlock freedom?
Because I've said something more general. In the present case, we have no deadlock in the abstraction, but it might be in some other system, we might have some deadlock in the abstraction.
You may want it. It may be desirable to have.
Yeah, sometimes.
Deadlocks.
Yeah. If we have deadlock in the abstraction, then this is relative deadlock freeness. Okay? And so what we have to prove is this, and I agree with you that in our case, the concrete guard, the abstract guard are true already. Okay, so there is no need for this one. Okay, so this is what we have to prove, that essentially the disjunction of the abstract guard implies the disjunction of the concrete guard. Now, what is interesting with this is that you remember guard strengthening. Guard strengthening was working the other way around. A concrete guard was stronger than an abstract one, and here we are going the other way around. So in fact, we describe with this relative deadlock freeness, we describe the limit of our strengthening. Because we could have strengthened the thing so much that we put a false guard, okay? But it is not allowed because if we have this, we have no relative deadlock freeness. Yeah?
So this allows me, for example, to take an abstract event and refine it so that the new concrete event is only enabled like half the time of the old, but add another event separately, which I guess is sort of what you did in the bridge, that sort of takes over for the other half.
Of course,
right?
of course.
And then together they work.
Of course.
It was not done in the case of the bridge, but in general.
Not exactly done.
Yeah.
But you could in general.
Yeah. And another possibility is here I have refined each event by an event, but it's also possible to refine an event with 2 or 3 or more, and then distribute the guard precisely exactly what you say.
How do you introduce sequencing among events?
Not now.
Okay.
Not now.
One thing at a time.
One thing at a time. But I can tell you a few things about it. I have not introduced loop. I have not introduced semicolon. I have not introduced ifs and else. Okay. Yes. But if I have time, I will develop the way sequential program with loop, ifs and else, and things like this are defined. So how could we go from a bunch of events to a program with this? Okay, that's a question.
Yes, actually, that is the question.
Yeah. Not now.
All right.
Not now. A bit later. Okay. Wait. So this is a relative deadlock freeness here. So we know disjunction of the abstract guard, disjunction of the concrete guard. So it is not very difficult to. It's a bit boring because we have a goal with many disjunction, but it's doable by a decent prover. So we have proved everything. So summary of the refinement: for old events, strengthening of the guard, concrete invariant preservation. For new events, refining the implicit event skip, absence of divergence, and for all events, deadlock freeness. Okay. So we have now a bunch of proof obligation. Again, they are part of the proof obligation generator, and the proof obligation generator generates automatically all these things. And here is a summary of the proof obligations. So the state of the first refinement is just this. You recognize ABC, the gluing invariant, the invariant about the fact that the bridge is one way only, the variant, and the constant D and the ABC. And I have not copied here the axioms for D because they are implicit. And here are the events of the first refinement. So we have the old events, and here the new events. Okay. And now we can go, and we have some proofs at the end. When is the end, by the way? It's now.
Now.
Okay. So we stop. We should stop now. Okay.
Maybe then. So we're going to continue next week with. We think it's going to be Tuesday and Friday, and we'll pick up right here.
Yeah. Okay. Thank you very much.
Great. Thank you.